Okay, let's try a different type of substitution here. When we have the square root of x squared plus a squared in our integral, the recommended substitution is x equals a times tangent of theta. And of course you choose the theta between minus pi over 2 and pi over 2 because that's the domain of the restricted tangent function, and really you're making the substitution theta equals tan inverse x over a. The dx becomes a times secant squared theta d theta because dx d theta here is a times secant squared theta. And the square root of x squared plus a squared becomes the square root of a squared tangent squared theta plus a squared, which is a times the square root of tangent squared theta plus 1, which is a times the square root of secant squared theta. Remember, secant of theta is 1 over cosine theta, so that's a times the absolute value of secant of theta, which is just a times secant of theta in this case because we've chosen the angle appropriately. Let's try it out. Let's try the integral of dx over the square root of x squared plus 4. Well, the recommended substitution is x equals a times tangent of theta, and a here is 2. So if we let x equal 2 times tangent of theta, then dx is 2 times secant squared theta d theta, and the square root of x squared plus 4 is the square root of 4 times tangent squared theta plus 4. Pulling out the 4, we get that's 2 times the square root of secant squared theta, which is 2 times the secant of theta because the angles are between minus pi over 2 and pi over 2. Well, let's switch everything in the integral to thetas, and of course it's very important to remember to switch the dx's. That's a pretty common mistake on exams in this particular type of integral. The integral of dx over the square root of x squared plus 4 is the integral of 2 times secant squared theta d theta, that's dx, over 2 times secant of theta, which is the square root of x squared plus 4. And one of those secants will cancel and the 2's will cancel, and we're just looking at the integral of secant of theta d theta. And hopefully you remember from the last lecture how to do this, or at least the formula. This is the natural log of the absolute value of secant of theta plus tangent of theta plus a constant. Now, of course, we'd like to change that back to some formula in x's. We have theta is tan inverse x over 2, so we're looking at the natural log of secant of tan inverse x over 2 plus tangent of tan inverse of x over 2. And remember, tangent of tan inverse of something is always the thing itself. So we're looking at the natural log of secant of tan inverse x over 2 plus x over 2 plus some constant, and now we're going to try to draw a triangle, a right angle triangle, with an angle theta, which is tan inverse x over 2. So tangent of that angle is going to be x over 2. That means that the opposite over the adjacent will be x over 2, and of course the easiest one to construct is one with the opposite side of length x and the adjacent side of length 2. And of course this completely determines the third side, which is now the square root of x squared plus 4. We have secant of theta in this case is 1 over cosine of theta, so this is the hypotenuse over the adjacent. So this is the square root of x squared plus 4 over 2. And of course that is secant of tan inverse of x over 2 because theta is tan inverse x over 2 here. So we can replace that secant tan inverse x over 2 by the square root of x squared plus 4 over 2, and we have our integral is equal to the natural log of the absolute value of the square root of x squared plus 4 over 2 plus x over 2 plus a constant. For these types of integrals involving the square root of x squared plus a squared, the best substitution to make is x equals a times tangent of theta, and the story is always the same. Dx is always a times secant squared theta d theta, and the square root of x squared plus a squared always turns out to be a times secant of theta. So these calculations shouldn't surprise you, and then whatever else is in the integral, hopefully it just involves x's, which can be replaced by a times tangent of theta. You have a familiar integral here, the integral of 1 over x squared plus a squared, and if you make a substitution, you can transform it to the integral of 1 over u squared plus 1, which is going to give you the answer 1 over a tan inverse x over a plus c. And you could also use this method to solve that, but remembering that the integral of 1 over x squared plus 1 dx is tan inverse of x makes your life an awful lot easier here.